Hi, I'm Conor Houghton. I'm going to tell you how to calculate the mutual information for data where the traditional, the naive estimators fail and often fail badly. As a way of introduction, h of x is the Shannon's entropy. It's the amount of information in some random variable x or in some data represented by the random variable x. We can do it for y as well, h of y, the Shannon's entropy of y. We can do it for x and y together, h of xy, the joint entropy. And as you can see, the joint entropy is less than or equal to the sum of the individual entropies because there might be some overlap in the information. There might be this area in the middle where the information is shared. And so on the left-hand side, you have the conditional entropy, h of x given y. That's the information left in x if you know y. It's the information that you gain by learning the value of x if you already know the value of y on average. The same on the right with the yellow square, but that's the conditional entropy of y given x. And so you have this little bit in the middle, which is the shared information. It's the information that x tells you about y on average, or the information that y tells you about x. So here is the information that's left in x if you know y. And so this is the amount that knowing y will reduce the information in x. And the algebra that matches these diagrams tells us that the mutual information between x and y is the sum of the individual entropies minus the joint entropy. Mutual information is one of the fundamental way to measure the relationship between two random variables. It runs all through data science, more in principle than in practice. And you'll know, for example, that in machine learning, many machine learning quantities can be phrased in terms of information quantities. Many objective functions are information objective functions. In practice, though, the mutual information can be very hard to estimate. And it's easy to see why. This is the formula we had before relating the mutual information to the entropies. If you substitute in the actual formula for the entropies in terms of probability densities, this is the formula you get. The mutual information is the expected value of the log of the ratio of the joint distribution over the x and y space, divided by the distribution that x and y would have if they were independent. In other words, the multiple of the marginalized distributions. Now, let's talk about the correlation instead. Often when looking at the relationship between random variables, we use the correlation. It's the expected value of x minus its mean multiplied by y minus its mean over the two standard deviations. And when I say multiply, that would often be a dot product. And that's one of the things that's sort of ugly about this correlation function. It relies on these things being defined. In other words, it relies on it being possible to work out a mean. It relies on the existence of a standard deviation. It relies on some algebraic structure or inner product or structure between x and y. However, for all its ugliness, it's easy to estimate. If you have data, xi, yi pairs that you've drawn from your distribution, you can just plug them straight into the formula and average to get an estimate for the correlation. Mutual information, in contrast, is very beautiful. It relies only on quantities that exist. If you have probability distribution, there is a probability density. And so this quantity in principle always exists. In practice, we don't know, or often don't know, the probability density. And so if we have lots of xi, yi pairs, it doesn't mean that we can average them to get an estimate of the mutual information because we don't know p of xi, yi, or p of xi, or p of yi. And so estimating the mutual information comes down to this problem of estimating the probability densities. And that can be hard. You know, what you do is you make some sort of histograms, you count the number of points that fall into a little square or a block and use that as an estimate of the probability density. That doesn't work very well if you can't well sample the space. If the space is very high dimensional, the number of little histogram blocks will become huge, immense for large spaces. Or you might not have coordinates at all. Lots of data types that we're interested in don't have nice coordinates. Event series, you know, the arrival times of something like spike trains that help communicate between neurons. They don't have coordinates, but they do have a metric, and that's the point of view that we want to take here. That data often comes with a metric. Two pictures, doing mutual information estimation for images could be very hard because it's a million dimensional. Trying to divide the space, million dimensional space up. Well, assuming this is 1,000 by 1,000 pixels, dividing that space up for doing histograms will give you an immense number of histogram blocks. You need an immense amount of data to sample it. But you know, we don't think of pictures in terms of their pixels. We think of them in terms of some measure of their similarity. And for many data types, we have a notion of similarity. And in fact, the similarity expresses the property of the data that we're interested in and that we're interested in using for calculating the mutual information. Functions, functions are very interesting for mutual information, for data science, fluctuations in stock market prices or whatever. It's an infinite dimensional space, but it's very easy to measure the distance between two data points. You could use the mean square error or one norm or whatever. So data often comes with a similarity. That's a much more basic notion than the coordinates we normally use. And so our aim here is a much more natural notion, and it's robust against increasing dimensions. So our goal here is to come up with estimates for these probability densities that use the metric structure of the data and nothing else. Now, to talk about this, I'm going to use the example of a dartboard. The game of darts, you throw an arrow at the board, it sticks in. There are certain rules that determine who wins, and they incentivize firing it one part of the board rather than another. So in the dartboard, there's some probability distribution, a function of X, your position in the board, which you can use to calculate how likely the dart is to have landed in a particular part of the board. And if you buy a used dartboard, which you can do reasonably cheaply, you have a sampling already performed, because you've got these little holes which show you all the places the darts have landed in the past. And you can see, the dart is more likely to land here than here, because this is a more desirable location according to the rules of the game. And to remind ourselves of what probability mass does and what probability densities do, the probability that a dart will land in some region B, well, that'll just be the integral over that region of the probability density. And the expected number of holes in that region, the expected number of events lying in the region more generally, is given by the probability mass multiplied by the total number of holes. And we can now use that, in fact, to estimate the probability density. So if the region is small enough, or if the probability density is varying smoothly enough, and you can always make the region quite small, then the probability mass, it can be estimated by just multiplying the value of the probability at any point inside the region, because it's constant, by the volume of the region. Similarly, we can estimate the expected value of the number of holes in a region just by the number of holes in the region. So the number of holes in the region estimates the expected number of holes in the region, and that in turn is estimated by the probability density at a point in the region, multiplied by the volume, multiplied by the total number of holes. And so if you take all the red stuff on the right-hand side there, divide across by it, that gives you an estimate for the probability density. And there's two parts of the estimation there, assuming that the P of X is barely varying. That makes you want to have the volume small. The hope that the number of holes is a good estimation for the expected number of holes, that makes you want to have the volume big. And somewhere in between, there'll be a good size of the volume. And using that, you have an estimate for the probability density. You can use that estimate inside the formula for the mutual information, and that gives you an estimate for the mutual information, a type of estimate known as a Kozachenko-Leonenko estimator. What we're going to talk about is a KL estimator, where you're using only the metric, only the distance structure on the space of data. But before doing that, we'll just do that calculation quickly. So for this little region here, the probability density is estimated as being 4, because that's the number of holes, the number of events inside the region, divided by the volume of the region, which is the fraction of the dartboard represented by this little circle, multiplied by the total number of holes, which I haven't counted, unfortunately. The problem is that that's assuming that we can work out this volume. That's easy enough for a dartboard, two-dimensional space with coordinates. You just integrate the coordinates. But if you don't have coordinates, or you're not wanting to use the coordinates, we've decided to try and do this using only the metric, you can't use that volume measure. And so what volume measure can you use? Well, in fact, any probability space has a very natural volume measure given by the probability mass itself. In a sense, it's the canonical volume measure on the space of outcomes of a random variable. And so what you're saying here is you're defining the volume of a region as just being the probability of finding the data in that region, the probability in this case of finding a dart in the region. So that satisfies all the rules or properties you might expect a measure of volume to have. And so the volume, we're going to use that, the volume of a region B now, is the probability mass of that region. And so we can actually estimate from the data the volume of a region just by counting the points, because the probability mass is the number of points data points divided by the total number of data points in your sample, or in the case of the dartboard, the number of holes in the region divided by the total number of holes. And so this little region we had before, what would its volume be? Well, its volume, according to this volume measure that we've decided to use, is h over n, where n is the number of points, in this case 4. And so we'd say that that little volume had, that little region had an area or volume 4 over n. However, you might worry that we've gone around in a big circle, and in a sense we have. If we go back to our estimate for the probability density, it was given by the number of points in the region around the point we're interested in, divided by the total number of data points and the volume of the region. And if you plug everything in, that's going to be h over n multiplied by h over n, or divided by h over n, and that's equal to 1. In other words, we've chosen a volume measure that makes the probability density a constant 1. If you plug that into the formula for the Shannon's entropy, that tells you the Shannon's entropy is 0. In other words, we have accidentally trivialized the entropy. And you know, entropy, as it turns out, isn't a well-defined quantity. It depends on the measure. And we've seen that here. We've chosen the measure, in fact, that trivializes the entropy. And that seems like a problem until you remember that mutual information is well-defined. It doesn't depend on the measure. And what actually is happening there is that we have two probability densities for mutual information, the joint density and this multiple of the two marginal densities, the density that XY would have if they were independent. And so what you can actually do is use one of those probability densities as the volume measure. In other words, you end up trivializing those and you estimate the other by counting points. And so there is a strategy using this counting points both for estimating densities and for estimating volumes that gives you a formula for estimating the mutual information. In fact, that formula is here. So it's a very straightforward formula. You've got lots of data points, you average over the data point, and for each data point, you find in the X space, the ball with the H nearest point. So for given X, you just find the nearest points according to your metric. In the Y space, you do the same. This is a different ball in the Y space of the H nearest points to Y. And then you work out the number of points that are in the intersection, because of course the points are being sampled as pairs. You're in the joint probability space, you're getting xi, yi pairs. So how many points are there in the intersection? You count that, you plug it in, h squared is just obviously this value you're using to determine how big the regions are, and it's the total number of points. You average over all points, and this gives you your mutual information. So that's the formula. That is an estimator for mutual information, which depends only on the metric and which should be robust and useful for data sets where there's no coordinates or for very high dimensional data sets. Now it does, just here's a quick picture. So here's the Y space, could be, have a huge dimension or no dimension at all. Here it's just one dimension. The gray vertical line are the H points, in this case H is 7, closest to the point that we're now using in the average. Here the same for the vertical line, gray region, 7 closest points in the X space. The intersection is 4, and so there'll be a 4 here, 7 squared there, and the total number of points there. That's the estimator. A couple of technicalities. Estimators of mutual information are always biased, but one big advantage of this formula is you can actually work out the bias explicitly. I haven't shown it here, it's just some hypergeometric function, but you actually can correct for the bias explicitly. And second, you have to decide this smoothing parameter, this H, how big your balls are, sorry, how large a region you're using. And well, there is a sort of a heuristic for finding H, so all is not lost as far as that's concerned. Here's just a sort of quick example. This formula works. It's just anytime we've tested it on different sorts of data, it seems to be a good estimator, and I recommend that you try using it. Here there's X and Y, there's some parameter mu which determines the mutual information between them. So each value of mu corresponds to a different data set, and the black line is the estimate of the mutual information using this new estimator. We also estimated it with the old-fashioned sort of histogram type estimators, again with some sort of bias correction, although it's not analytic in that case. And we see that with 125 times as much data, the old method is as good as the new one, but with 10 times as much data, there's a clear difference, and the old method isn't catching the mutual information. So thank you very much. Here are some papers where these things are described. Here's my email address. If you're interested in using the estimator and you want help, do get in touch. Thank you very much.